This presentation is titled Simplified Machine Learning Workflows Overview. This is a Raku spin of the presentation I gave with the same name at the Wolfram Technology Conference last week in October 18th, 21st, 2022. My name is Anton Antonov. I'm a senior research scientist. I worked for Wolfram Research 6, 7, 8 years and 8 years. And I've been using Raku for say 3 or 4 years. So in this presentation, we're going to see how I use natural language template engine and domain-specific language translator to generate executable programming codes for different languages, Python, R, and Wolfram language. Wolfram language and Mathematica are going to be used as synonyms in this presentation. The workflows which are covered by these functionalities belong to the machine learning subcultures of data wrangling, classification, regression, latent semantic analysis, and recommendations. So again, this is the Raku-centric version. So I would like to manage certain expectations here. So well, we're not going to become specialists in machine learning just by watching this presentation. The other is that hopefully I can give the main message, if not within 5 minutes, but say within 10 minutes. I'm not going to review the machine learning workflows, not in the way I reviewed them in that presentation. I have done also this elsewhere. I am going to browse through them. I'm much more interested in discussing the general topics, which say I didn't have that much time to allocate in my presentation at the Wolfram Technology Conference. And again, this is still an advertisement presentation. So it's somewhat of a call for collaboration in whatever kind of I'm doing here. You can see my presentations at the Raku conference 2021 and 2022, which covered this material. 2021 is more closely related to what we're going to see here. And 2022, this was like say in August, like a few months ago, it was much more about duplicating these functionalities, which we're going to see in say Mathematica or Python or whatever, duplicating them in Raku. All right, so generally speaking, this project has several types of goals. So I want to speed up the coming of the next artificial intelligence winter. I want to replace expertise with enthusiasm, more I guess humanistically. The future is already here. We just need to make it more evenly distributed, say with system like the one I'm going to show. And more cynically, I want to facilitate the professional life of code baristas, people who just serve some code and get paid for it. A very important principle I have followed initially with Raku is clothes have no emperor. So it's not emperor have no clothes, it's the clothes have no emperor. And in general, I was following this. This was my Raku policy for quite a while, but lately I've been trying to actually use Raku also to do machine learning. So we can say that 60% to 85% of all machine learning workflows belong to these subdomains: classification, regression, latent semantic analysis, recommendations. Classification belongs to supervised machine learning, and the rest they belong to unsupervised machine learning. Some people have successfully convinced me that data wrangling should be part of this. Data wrangling is not a machine learning workflow per se, but most of the time machine learning or data science practitioners, they do data acquisition and data wrangling. All right, so here are some examples. So you can see I have this fairly concise generic commands. I'm using a function called concretize, which belongs to this NLP processing template engine. This is using neural networks. It's not using Raku, it's using neural networks implemented in Mathematica. There's some computational workflows classifier which is being downloaded when I first execute this function. So each of these commands, each of these commands have been classified into a specific workflow. And you can see the first one, it's about classification, the second one about latent semantic analysis, the third one about regression. So what is interesting to note is that there is a Pareto principle within the Pareto principle. So within each of these machine learning subcultures, 70–80% of the time you are using just one workflow, something like this. But you might want to have different, say, parameters, number of topics, or different, latent semantic indexing functions, or in classification you might want to split the data, not just say with 75%, but say with 80% and so forth, and you might be interested in other measurements and other classifiers, or classify ensembles. Alright, so the simplification in this project is done in two main ways. There's an attempt to see what is invariant within each of these subcultures of machine learning. And so these invariant workflows within each subculture extracted, and there's a flowchart and there's a monadic package for each of them. Monadic packages are not necessarily, but they actually help both communicating and also making some bigger claims about what these projects accomplish, what this machine learning workflows attempt to do. It happens in a more sound manner if we use monadic packages. The other simplification is that we produce executable code into Python, R, and Wolfram language, sometimes into other languages like Julia, Raku, and Swift. I can claim that these workflows, the way they have been abstracted into natural language commands and into monads, and the correspondence between the natural language commands, grammars, and the monads, the software monads, it's both operational and theoretic. And this actually, ideally, I should be able to illustrate this. All right, so I have made variety of interfaces to this system, and I have demonstrated this in several ways. So here, while is this being, I'm going to reload it, but while it's being reloading, I'm going to discuss some of the elements here. So there's a resource function which I can use, and let me see, can I show you the resource function? Mathematica has this ability, this repository of Wolfram function repository of functions submitted by users, right? And so this function, you can see it does generate these workflows. It actually goes to a certain web interface, and I'm going to show this web interface here. This is what you see. What we see here is some web service I have written with Raku-CRO, and the NLP template engine is being invoked through the Wolfram engine, but the actual grammar parsing is done, of course, with Raku. Now I have another application, right, on a different server. This is the Shiny Apps server. This is what you see here, this web page, which connects to this web service. My Raku-CRO service is in some droplet in DigitalOcean. I'm renting a server here. And what you see in my presentation, it's a Mathematica notebook that uses this web interfaces. Now I'm saying that in this Mathematica notebook, I'm going to be using this interface through this Mathematica function. I mean, obviously, this is happening here within this whatever kind of documentation of that function I was showing. I have shown this in the past, how this can be done using Siri shortcuts. There's also command line interface to the function. There's no reason to use web interfaces. We can do this through the command line interface. I'm going to show next, but let's see here this example. We're going to generate some code. This is data wrangling code, and since I said this is going to be a Raku spin, here is the Raku code for this. All right, and we can, if you go to this interface, you can find examples for other machine learning workflows. All right, so So here, this is the command line interface. So here, let's actually put Wolfram language. So this is going to produce Wolfram language code. It's this double. If I copy and paste, let me see. Is this going to let me? Actually, this should let me do it. I just need to do this, right? So the implementation DSL translation, this is a Raku function. The way it is implemented, but if whatever code is being generated, it's put automatically into the clipboard. And so I can use the web service. Basically, this this command line function, it's using the web service I was discussing here, right? And you can see I do have some. I return a JSON record when that is invoked. Interestingly, importantly, it can have a user ID, and this user ID can be used to further specialize the outputs. All right, this actually, let me see, can I do this easily? I think I might be missing some functionalities being loaded here, but that can be relatively quickly remedied. And so, okay, so there's a process here which I'm going to invoke. This is the Raku process. What I'm saying is that instead of just using, let me return back to this list here. There can be dedicated cells within the DSL mode cells within the notebooks. So this is what this command is showing. And so here you can see this is generating latent semantic analysis pipeline code, monadic code based on this command. I mean, I can execute this. If I'm executing it, right, you can see something is happening. It's using abstracts, which are like, say, nearly 600 abstracts. This is from Wolfram Technology Conference abstracts. And yeah, we're executing this. All right, so here, similarly, this here, it's an executable cell, executable domain-specific language cell. And let me actually make it non-executable one. This is with this light blue. This is just going to generate the code, right? And now if I have this data, df Titanic, this is going to produce the code, right? And it's very likely that I don't have the actual data being loaded. What I'm going to do here is I'm going to make a Raku cell, right? And I'm going to use a function called example dataset and put this Titanic data. So here I'm going to do ds Titanic. Actually, are we using ds or df? Anyway. All right, so we have df Titanic. So I should be having this data here. This is Raku, right? And now here, if I generate the code and execute it, I should produce something that makes sense. Yeah. All right. So far so good. Now what I'm saying is that instead of having the code first generated and pasted in a Raku cell, this is what was happening here, I can have it directly executed, right? So this is with this light yellow DSL cell. All right, I have demonstrated this before, but having this connection reliable and fast is very important, and I plan to improve it further in the future. So how is this development work done? We start with, studying certain problem domain and thinking about it. Then we develop some software monads. That's not necessary, but again, developing software monads really helps about different types of crystallization, if we can say, about what this problem domain, what are the main concepts and workflows and challenges. Parallel to that, or after we have done the software monads, we develop a set of grammars, or a grammar for the natural language commands for this problem domain. I don't think this can be done, this is done in parallel in a sense, because obviously in order to make the software monad or the software packages, you need to be able to verbalize what you're doing. I mean, hopefully you can verbalize it. So in some sense, I would say these are interdependent, or some kind of iteration between all this is happening, and different people might have different inclinations how they concretely follow this. But in my opinion, all these three elements should be followed. They always be into the mix. So after we have done the monadic packages and the grammars, they're closely related. So a sequence of natural language commands is going to resemble fairly well a sequence of programming code. This is more or less what I'm showing here. So I'm claiming, or what I'm saying right now, is that this sequence of natural language commands resembles these commands which are in the monad. And unit testing is very important. This system should be made with keeping in mind that it's most likely to fail. So it should be made to fail, and failure should be handled gracefully. And after we have made a single line interpreter, which is the first marriage between the monads and the grammars, we can actually do some second order commands, like say do a typical pipeline for latent semantic analysis. Instead of spelling out all of these elements here, like how I did it here, I can just say, yeah, take a typical command, or just apply my previous or my most frequently used latent semantic analysis pipeline into the data a abstract 8 or something like that, right? Then we can further make a conversational agent for this workflows. I have to say, for the core machine learning workflows, conversational agent didn't seem to be that useful. Having fast and reliable generation of workflows like this was more important. The conversational agent itself become more important for the second wave type of applications. Like imagine you want to make a recommender system for recruiting, or for food preparation, or I don't know, managing of store warehouses or something like that. So but then my users become something else, right? In general, with the machine learning workflows, the users I target, not people off the street, but say people who have technological thinking. And we say this food preparation agent, right? I'm targeting people who might be, just want to learn how to cook, not necessarily to learn also how to do machine learning. So this is an illustration of the principle of clause have no emperor. So in orange, this is what the system knows. It does have access to a recipe recommender and meals recommender. It has this interpreter. This is sous chef Susanna conversational agent. It's a parser interpreter, or conversational agent, or whatever. It's using Raku grammars. It's using machine learning Raku grammars. In blue, I'm showing databases which were operated upon this recipe recommender and meals recommender, but we don't necessarily know what these databases are. So there's an interesting question here. What part of this the system is aware of, right? I can, with what I was showing earlier, my Raku system just generates workflow codes for these recommenders, right? And that's it. It doesn't need to know about the recommenders at all. But if you do have the recommenders, their outputs can be used to further specialize, or further do some recommendations. And again, you can still have some data which is not necessarily known by the system, but it is leveraged in some way. All right, so I've been showing basically at this point two systems. One is the NLP template engine, which is using neural networks implemented in Mathematica, and the other one is using context-free grammars. I'm a big fan of the context-free grammars, but when I show this system to people, they tell me, well, I'm probably doing something very stupid, because using grammars, it's very, it's too much manual work, and it's too slow, and so forth, right? And I can get much better results, better and faster results using neural networks, like say GPT-3, BERT, and so forth. Well, no, we don't. And to some extent, that's why I made this NLP template engine, to just, not just to argue, but to be able to compare. Neural networks, when it's applied in the way I'm applying it with this NLP template engine, it's basically a question answering system which interrogates each of these commands in a variety of ways, and then certain templates are being filled in. This is why I was saying it's important that we have Pareto within Pareto. If, say, within the 70-80% of all machine learning workflows, in those, we have identified those workflows, and within each of them, we have the one which is most frequent, like 70% frequent, then I just need to fill in certain parameters, like filling in a stencil, filling in a template. This is what I'm doing with the neural networks. This is the assumption. Well, that works more or less nice to a point, but if you do data wrangling, you just cannot do that. With data wrangling, you actually need to specify the sequential order of the in the individual specifications. It's actually quite important, right? And so you need to, for data wrangling, obviously we need to use something like context-free grammars. In order to kind of compare the two, we can do variety of experiments, but what is important here is that these systems complete each other. We can have a fallback mechanism. I can use the context-free grammars as a fallback mechanism to the neural networks implementations, and the other way around. Now, I would say with neural networks is probably developing the generation of the codes is probably like 5-10 times more like 10 to 100 times faster. It can be quite fast. The problem is that this is an heuristical approach, and as any heuristical approach, it breeds special cases, and it's not clear whatever kind of system you have figured out, combined to generate your executable programming code. Is it going to work with the next versions, with GPT-4 or BERT2, or this question answering system I mentioned, with 1.1 version and 2.0 version? All right, this is using the DSL translation function I was showing earlier. This is the monadic pipeline for the classification, and we can see here with this monadic pipeline, I mean, it again corresponds to the commands I have shown here. And hopefully, let me see if I execute it, what's going to happen. So yeah, I mean, we're using the DS Titanic data. We split it with this ratio, 76 for training, and I guess the other for testing. And then we show accuracy and precision, which was requested here. And then we show receive operating characteristic plots, right? Which basically can help you make a decision how good the classifier is. And with what parameters, what thresholds to kind of to use the classifier. Titanic data, if you're not familiar, Titanic data has a column passenger survival, and this is what we're classifying into or for. All right, now what is interesting is that if I can translate natural language like English into programming code, should be able to translate it to another natural language. And so we can see here this translation to Russian. So this is my next example. This is a multi-language system in both senses. I can put commands, specify natural language commands in both Bulgarian and English. This is what you see here. This is Bulgarian specification of a latent semantic analysis workflow. If you don't speak Bulgarian for some reason, you can see it here. It is the same command is translated into English. So we're making a document term matrix. We're extracting 30 topics, and then we show some thesaurus and stuff like that. Actually, let me execute this first. And so this is executed by default. The result is being placed into the command line, and I am basically executing this. So you can see this is basically executing. It's making this document term matrix and etc. I'm using again this abstracts data which I mentioned earlier, and you can see I'm asking for statistical thesaurus of the words notebook, function, and neural. And so you can see here notebooks, and actually, they should make quite a lot of sense, the statistical thesaurus. And if you look at some of the individual topics, like say topic 25, course, package, teachers, materials, creation, so forth, students, yeah, I mean, obviously what it is about. If you look at, say, let's see, can we spot something about neural networks? Yeah, like say topic 16, neural training, learning networks, network tasking, etc. So here the words are not stamped, you know, so it's very good to actually show, let's say, network and networks together. If they were stamped, this would have been one word. I'm not going to go in such detail with the, with the rest of the presentation when it comes to the machine learning workflows. I already explained this. This is just different here, but we can dictate to this system. We can use Siri. I have demonstrated this. You can find the video called Doing It Like a Crow. Not just for, this system is not just for machine learning workflows. This is what I want to show. This here is generating epidemiological workflows, and I'm not going to go too much into this, but in some sense maybe you should believe me, but it's following exactly the same principles. It's just any computational workflow can be done in the manner I am describing. So what is happening here is that I'm setting up with a certain model. I'm setting up some epidemiological simulation. I'm having 100,000 people who are susceptible and have only one which is being contagious, has the pathogen, and then I have different rates for the you know, how people contact to each other, and then I want to simulate this for 240 days, and this is what we see here. All right, so this was my first choice of a talk for that conference at Wolfram. My first choice was becoming the best Python programmer I know. And why I'm mentioning this at all? I said this is a Raku spin. Well, the reason I became the best Python programmer I know quickly is because I was fairly well versed in many of the concepts by learning Raku for like 2-3 years. And so I'm going to show here a couple of comparison columns before and after. And I thought Python is a stupid language, and this was its biggest selling point. Turns out it's more like deceptively simplistic. And I thought, again, Python is good as a glue, but no, it's good for moderate size projects. And the object-oriented part in Python, I thought it's pure. It's not. It's bolted on, but I like that. And yes, most of the reasons, or anytime I find Python extremely convenient, it's because it's interfacing certain workflows already implemented in C and C++. So Python, being some of these observations here, and probably I'm biased, Raku is not like that. I wouldn't call Raku stupid. I wouldn't call it deceptively simplistic. Quite on the contrary, I would say. Yes, I can use Raku as a glue language, but another thing is that I think Raku can be fairly adequate for large size projects. It's just when I implement machine learning, none of the machine learning projects I implement in Raku are that big. In some sense, they cannot be. They're already quite specialized. All right, so I'm not going to go further with that. We're actually going to see some other comparisons, which I'm probably going to refer to, how this part here in Python, I decided to, which I did last year, 1 year ago, I decided this summer, 2022, to replicate my Python implementations in machine learning, to replicate them in Raku. And so here, yeah, I was mentioning, I'm writing a book called Simplified Machine Learning Workflows. I wanted to write a book, still do, how to be a data scientist imposter. Very quickly, I realized that the main message, how to be an imposter, is going to be kind of put into some sort of a, confusing fog if I spend too much time discussing the machine learning workflows, the actual know-how. So the know-how was extracted from here, and this is more like, say, the meta part, philosophical and methodological. This is the actual computational workflows, how we specify them, how exactly they're applied, what we're actually doing. So I'm using monads and object-oriented programming for a variety of reasons, and these are not necessarily popular popular methodologies in the Wolfram language. That's why there's a third book, which is 90% finished at this point. That's not important to some extent. In Raku, we can do both object-oriented and monadic programming fairly easily. But this is the big picture, and I do plan to finish this book, say, by the end of 2022. Classification workflows is more or less everybody understands it. This is the simplest type of machine learning. This is supervised learning. It is the first non-trivial monad I implemented. As I mentioned, I'm not going to go through the actual workflows, but I am going to say that whatever I mentioned earlier, that the workflows have been ingested and digested by me, and I have produced monads and this kind of diagrams, flowcharts. This is how the simplification is being done. Plus using these grammars, right? This should be enough of a simplification. One important thing to mention is that when people see the systems like, well, why should be using your packages? So basically they're saying in this, I thought I evaluated this function. Okay, we're saying why should we use the packages you have implemented, right? We want to use the built-in commands. Okay, yeah, this is the built-in commands. It's not easy or clearer exactly how you do it with monads. You know, whatever I was showing with monads, it's simpler. And but you know, again, you know, like if you have designed the monad, if you have figured out what exactly are the workflows, the actual implementations, they can be done in a variety of ways. This is worth explaining a little bit more. So I'm going to go to my repository here, and I'm going to find out, yeah, you can see that I've been intensively, mostly for the conference, doing different type of machine learning workflows, recommender workflows, latent semantic analysis, regression, data query workflows, and here somewhere I should have classification workflows. So what I'm saying is that in Raku, this is just very nicely done. I mean, I can have my my actions. This is for the monadic pipeline, and I can have it also for the system pipeline. Another thing here I would like to mention is that I have made certain entity parsing packages, which hopefully I can show or easily locate here. I'll just search for it. So all of this kind of specific, I would say, measures, or this is for the measures, right? This is for the measurement names. But I have different phrases with which I can specify all these peculiar classification workflows, measurement names or specifications, and how they translate to actual entities. And I'm using this into my classification workflows. If I show you the actual grammar here, it is using this entity. It's using this entity machine learning entity names in order to do the actual parsing. So the architecture here, what is happening is that let me zoom a little bit. So I have the different workflow commands, right? So yeah, like loading of data, splitting of the data, you know, doing dimension reduction, making classifiers or classifying symbols. Then we actually what we specify with the measurements and so forth, right? So this is generic. You can see I don't have any kind of concrete, except this. I don't have any kind of concrete terminals here, very rarely, right? They're all pushed out into some other files. Like I have this templates, and from these templates I actually generate the actual classification phrases, right? And so forth, right? Now my actions, you know, they're basically, you know, I have the monadic one, I have the non-monadic one, which is this system one. And if I want to, I can have also different languages. You can see classification right now, it's only in Wolfram language, but I have also, I can have actions which translate English into, say, into Bulgarian. Of course, I can translate English also into English, and that's important. But this means that if I have some Bulgarian specification, I can also translate it to English. So this is why all of these monadic implementations, although we start with English, it's literally in the name, we also know how to translate that code into English. All right, so these are special features for the classification monad, which is important, but I'm not going to go here. I already discussed latent semantic analysis to a fair degree. Again, we have this flowchart, which basically says, what is a typical workflow, and I already went for that. That's why I'm going to recite it. We just take the data. We apply latent semantic indexing functions. We start extracting topics, examining statistical thesaurus, or examining the topics, and so forth. If we have acceptable results, we declare victory. If we don't, if we do too many executions, we give up. Again, I already demonstrated this. It's actually very interesting to apply latent semantic analysis to images. I'm not going to give too many explanations here, but one, it's more like from a software engineering perspective. Applying latent semantic analysis to text, you can get results, and with examining these topics or whatever I was showing, okay, well, you see that they work, and maybe you'll agree that your implementation works. If you apply it to images, if you're able to approximate images you haven't seen with the topics you have extracted through latent semantic analysis and make a classifier, well, first of all, visually you can confirm have you implemented the whole thing correctly, and second, it's just useful to use it as a classifier of images. This is the quantile regression workflows. I'm surprised people don't drop any kind of regression after they see quantile regression. I'm not going to expand too much on this, but let me see. I think this example here, in this example here, I'm doing both quantile regression, typical quantile regression. So I'm taking the data, which is temperature data from Orlando, Florida, and I'm showing some echo summary, echoing some summary of the data. I have done the quantile regression already and the linear regression, this with fit, but I'm also doing neural network regression, and I'm stopping it because it's taking too long. Now you can see in this plot here that I have all three types of regression I have specified using neural networks, using least squares. Right, this is the standard regression, and using quantile regression, in which I'm actually using some, some probabilities for the curves here. That's actually very useful because this means I can reconstruct the signal on a given timeline with quantile regression. None of the other regressions give you this capability. Actually, you can do neural network with the neural networks. You can do some sort of quantile regression, and it's the same thing actually, and you can make an analogy, but and basically, why use neural networks if you can just use quantile regression? It's very interesting to draw an analogy between the neural networks and quantile regression. There's a strong analogy here. I'm not going to go through this, but actually, why not? So the big secret here is that with neural networks, usually you cannot interpret your results very easily, what's going on. And you might want to overtrain your models in order to kind of see where the boundaries of your modeling activity or modeling approach are. And so I'm not using neural networks here. I'm using quantile regression, but you can see it's actually probably, I would say this is probably the good approximation with 12 nodes, right? And I might play with the actual order of the order of the basis functions. So in the basis functions we use, I'm using B-splines with order 2, what I was showing earlier. Yeah, I mean, there's similar type of selection for the neural networks. As I said, overtraining is to do in both cases. In linear programming is used as an optimizer for this quantile regression implementation, and there are a variety of optimization algorithms used by neural networks. So, I mean, this is the analogy. I've mentioned this several times. Other programming languages can be used, not just say Mathematica, but Python, R. And for what I was showing earlier, classification I have only implemented in Wolfram language. Yeah, I mean, it's in my to-do list to implement it in, say, for Python, and now it just hasn't been that important. But latent semantic analysis, quantile regression, and recommendations I have implemented in quite a lot of languages, some of this Raku included. And so this is what I was just saying. Recommender systems is something I do fairly often for a variety of reasons. First of all, 60% of the time when I'm hired as a data scientist or senior data scientist, people want me to do recommendations or recommender systems, but I also make recommenders as a first level regression, and that's a little bit confusing probably, but regression as a name is very wrong, right? Some scientists observed that the men who are tall have shorter sons, and he called that process or that observation regression. Something like that, right? If you read the history of statistics. But regression in statistics now, right? It means something more. So there are 3 levels of regression. The first level of regression is just to kind of find some dependencies between the variables. And this is where I use recommender systems. So quickly making recommender systems for the data at hand. It gives me a very quick way of examining the data and trying to learn it. Then the second level of regression is we try to find the most important variables into the system. And so, say in Titanic data for survival, turns out that sex is the most important variable. And then the third level is what exactly should be changed in these parameters or values in order to influence the system in a certain way. So you can see Raku is also included in this list, although I'm not using Raku for any practical recommendations. Practical meaning, like say industrial, like say warehouses or whatever, right? Or I'm using Raku recommender systems as classifiers for actually doing machine learning with Raku. This is one thing. The other is that Raku is like a reference implementation for the implementations in Java and Swift and Kotlin. All right. I think I extensively demoed this system in my Raku conference presentation 2022. This is the recommendation workflows. This is, as I mentioned, quickly specifying some recommender system and so forth. All right, this is related to data acquisition. Maybe because I've been promising this is going to be Raku-centric. So this function concretize. It's producing some. Let me see here. It's producing certain code, right? There's some wrong code here, like generators. For some reason the generator is I don't know, for some reason it decided that the correct response for this is the generators to be I'm not going to fight it. Actually, let's do this command here, right? Let's actually generate Raku code, since I've been mentioning it's Raku-centric. So if I do target language to be Raku, this should produce Raku code. And all right, and here I'm going to paste this code. This should complain, but let's execute it. Right, yeah. Okay, so I do have this random pet name function, which is what I wanted to specify with camel case for Mathematica, right? And this produce some data which I want to visualize, and this is going to be with 2 pretty table. And all right, yeah, so yeah, we can see Chen, Atticus, Abilene, Finn, Millie, Max, Puma. They do sound like pet names, and I requested 8 columns, although this generated only 7. Probably generated 8 columns, but 2 of them were duplicating the same name. And then I wanted 30 rows, and I guess you can believe me, but this is the case. So yeah, okay, I'm not going to try to convince you about the pet names, why the columns at this point we got 8 columns, but yeah, it's using random choice, meaning it's not just a sample of the available pet names. Sometimes the pet names can be repeated. All right, so basically, yeah, this is again, this is the using the neural networks type of implementation. I am interrogating this system, these questions here. I'm interrogating this command with different questions, and I'm filling in a template. So basically, I'm saying finding answers of the question, how many rows, and apparently it's 30, right? And then how many columns, and then what is the column names generator? It should have been this, but this system just returned it ignored the rest. And you can see with this minimum number of values and etc., 60 values, this is the response which is given here. All right, so the data transformation workflows, I have been discussing it a variety of ways, both for the Wolfram Technology Conference, the Wolfram U kind of talks, but also I did quite a lot of an overview of the data wrangling functionalities in Raku I have implemented and how they can be accessed through this system in the Raku conference talk 2022. What I want to mention here is that there is I actually have worked on this, just need to publish it, but this system can be seen applied to let me see where it is. Anyway, this system can be seen applied to variety of use cases, right? And so here this is a Raku Jupyter notebook, and it shows how to use the system to do data wrangling in Raku. So first I'm loading the data, and then you can see I'm using this these commands, right? We're using this to data query workflow code and so forth, right? So another thing here is that there is this is not exactly what I wanted to share, but all right. So there are also versions in Wolfram language. There is also versions in Python, right? So this is using Python, again, same thing. But like with this natural language commands, we can generate in pandas code. All right, fair enough. You might recognize this photo from my presentation at the Raku conference 2022. Again, most of the time I'm doing this. I'm not doing some huge pipelines of data when it comes to Raku, right? When it comes to using Raku. And I mentioned this for my recommender systems too. When I use Raku for data wrangling or for machine learning, it's actually for relatively small data, which is more to facilitate the code generation in other languages, or data acquisition, which data acquisition can be on some huge sets. But the actual data sets for the metadata of the huge data, right? For data acquisition is actually small. Say you have like 5,000 data sets. The data is kind of small, and Raku can be fairly adequate, fairly useful, and being able to do machine learning and data wrangling with Raku, it's really handy. This is the data wrangling workflows diagram. I'm not going to expand on it here too much. I have explained it in other presentations. all these notebooks I was showing, right, Jupyter notebooks, all of them, Raku, Wolfram, Python, they're following the same methodology, which is here. So this is one of the benefits of this. And here it's I'm showing data wrangling generation using the functions, interface functions I developed. All right, so again, I would like to mention this is a multi-language system, and this is just for the data wrangling, but this goes for anything else. And so from English or Bulgarian, we have an interpreter in Raku which interprets natural language commands in English or Bulgarian into executable programming code in these languages and corresponding libraries. Now, for example, if there's a base R, there's a tidyverse and there's data table. Here the ones in this dashed lines, they're not implemented yet, but I plan to implement them. In Raku, I have implemented the interpreters, the code generation for the package reshapers, which I have written, and obviously it's going to be very interesting to do it for Red and Dan. These are efforts by other people from the Raku community. Obviously, again, if I have made an interpreter to programming languages, I can translate this to natural languages. When I show this system for data wrangling, very often people say, can you translate Python pandas workflow code into these others, right? For some reason. I don't know why, but I guess, yes, we can. No, it's not high in my to-do list. I would actually rather do it for Raku first, but our tidyverse is the easiest to translate, to make this translation. So not just use domain-specific languages, natural domain-specific languages, but to use the domain-specific languages. These are the monads. Our tidyverse provides some sort of monadic access to data wrangling. And so, yeah, I'll probably do this fairly soon. All right, yeah, these are the notebooks I mentioned. You can, I was sharing this through locally on the browser, right? But you can find these notebooks in GitHub. They're already in GitHub, and yeah, you can see, yeah, whatever I was showing earlier. You can see it here. So workflow combinations, of course, very important. We might combine latent semantic analysis and classification. Let's actually show this. So this particular application is available at community, wolfram.com. So the task is to classify handwritten Arabic letters, make a classifier. And in this notebook I'm showing that using latent semantic analysis combined with nearest neighbors classifier, which means we can use a recommender system, beats some fairly well-known neural network, right? And I am not going to talk too much about it, but basically here we're using the latent semantic analysis pipeline. You can see it here. We derive some basis of images, and we are making some classifier based this reduced dimension. And the question is, because I said nearest neighbors, how many nearest neighbors should we use, right? And so there's like this systematic search with the testing and training data. Turns out that if you use the top 4 neighbors to classify the letters, so basically I'm finding the nearest neighbors of the Arabic handwritten images. I haven't seen into the set of images I have seen. This is from the training data. And then using this top 4 nearest neighbors, we make some, we basically produce some classification results, and we compare the confusion matrix, and we get fairly good results. For some of the letters, we get 94% accuracy or precision. For some of them, we get 60%. But say on average, we get 80%. And this seems to beat the neural network classifier. Now, this here, it's very interesting. Hopefully I can show it. it's actually, it's not shown in this way here, but this net chain, the way you see it here, it's actually a monadic workflow. Yeah, they're chained up and we have commas. We don't have this double arrow, which I'm using for my monadic workflows. But yeah, this is basically some sort of monad, right, which is being used here. And we start with, say, some image with 32 and 32 pixels, 32 by 32 pixels. And then we do whatever kind of transformations here, different layers, different functions, and so forth. Ultimately, we produce these classes. So we have 28 letters. So, all right, and it's not that important, actually the rest of the comparison, but it is in this particular case, it is actually interesting to note that, let me go to this comparison here in the top. And I didn't put the training times here, but yeah, I mean, this they're fairly comparable, the two classifiers results-wise. But the one I'm using with latent semantic analysis and nearest neighbors is like, 25 times or 20 times faster, and the times are not that big, right? So it's like between, say, is it 12 minutes or is it, say, 20 seconds or whatever, right? So, but in some situations, do you want to train your classifier for 2 hours or do you want to train it for 2 days? It's like becomes important. I'm not going to discuss other applications. The one with Chinese characters is kind of sort of similar. So I mentioned this earlier. So in Python, when I was doing this, right, in Python, I tried to do as much of what you see here also in Raku. So one of the best ways to learn the statistical abilities or functionalities implemented in a certain system for technological computations is to try to do random data generation. And so everything you see here, I did it also in Raku. So the data wrangling, code generation, yeah, did it both in Python and Raku. Random data generation, pet names, words, whatever, right? Except sparse matrices. And then example data sets. Yeah, you kind of saw earlier I was using the retrieval of one example data set. I would like to mention that sparse matrices is one of the ways the ability to deal with sparse matrix algebra. It's one of the ways I judge maturity of the systems. And much of the advances I did in Python, or the packages I implemented in Python, and the reason I implemented them quickly and they're effective is because I programmed this object called sparse matrix. This is an object that mimics something in the language S. S is the predecessor of the language R. So the sparse matrix is a sparse matrix with named rows and columns. All right, so the additional topics here, and this is probably one of the big things I should have discussed, not making this kind of so many digressions into, I don't know, software engineering. But the system allows you to own machine learning implementations, not to own machine learning implementations in variety of ways. Meaning you have the workflows, right? And with these workflows, you can generate code for variety of systems. Right now, it's say only Python, R, and Mathematica, but yeah, and Julia in some cases. But similarly, I can generate the pipelines and the workflow codes for Google Cloud Console or Amazon or whatever, or Oracle. And in those cases, actually, the pipelines, they're going to be through the command line interface, pipelines, which is just fine. Now, one interesting question is, and this is more specific to the things I was talks which are at this Wolfram Technology Conference, is what is latent semantic analysis better than using BERT, say, right? Well, yeah, I mean, in general, latent semantic analysis, the classical one, which is developed, say, 30 years ago, classical approach, it's better than the neural networks if you have like less than 1 million documents. And most of the time, this is exactly the case I have. So the tailor-made machine learning algorithms for specific applications, they they already beat whatever, whenever other, off-the-shelf, like say neural networks applications. It is important to be able to interface this system. Again, I'm discussing this a lot, and I already mentioned the sparse matrices, the sparse matrix object with named rows and columns, its importance. I'm not going to go too much through the history of the project here, but when I try to teach machine learning to people from the so-called digital humanities, right? Yeah, I mean, basically at the time, this was 2017, if you don't know programming, it's very hard to teach, but there is no reason to be so programming involved, right? And in general, right, I would say a language is low level if it makes you pay attention to insignificant details. And I would say, some of the data wrangling code you might see, or use, it just makes you pay attention to really insignificant details. Like if I find out, or whatever I was showing earlier, right? And if you look at, say, some of this code, right? I mean, do you really? So this particular kind of elements here, syntactical elements, they're probably not necessarily hard to learn, but you need to know them, right? And especially if you move from one language to another. And Mathematica, it's a good example of this, because Mathematica doesn't have a specialized monad for data wrangling. This is more like from this built-in language type of implementations, and this illustrates what I'm trying to say. I mean, you have some kind of quite a lot of special characters here. Now, if you know Mathematica, this is clear, right? But if you don't, right, this, in a sense, you need to know like this kind of syntactical elements. You need to pay attention to them. So so I decided to start making monads. At the time, I already was doing monads just to kind of show what monadically monads in Mathematica are easy to do. But yeah, basically implementing monads for the machine learning workflows, and then implementing grammars in Mathematica to do the machine learning workflows. That actually worked fairly well. One of the things here actually I would like to mention, I think it's worth mentioning, and let me do another demonstration here. Yeah, so in this conversational agents repository, I'm going to show some of the original grammars, right, which I wrote in Mathematica. Like I was showing classification. Let's actually go for classification. So yeah, I mean, of course, I can use some language like Mathematica, which is very Lisp-like, to implement grammar parsing. So I'm using a package I called functional parsers. Very similar package exists in Haskell, for example. I mean, some other functional parsers packages exist in other languages, like say Scala or whatever. Here though, you see these grammars, they're strings. This is Bacchus-Nauru form of the grammars, obviously very, very closely corresponding to what is we have in Raku, but in Raku that's built in. And it's very nicely handled. Now, I can have these grammars here in Mathematica in this way. I need to have a relatively easy to do, concise system to manage those grammars. You can see that I have a function in Mathematica which generates the parsers from the Bacchus-Nauru form strings, right? So basically all of these strings I'm showing here, they're being concatenated, or not concatenated, but for each of them the parsers are generated. Great, right? But if you have like say large number of grammars like what I'm showing here, and you have you want to do a multi-language parser, multi-language interpreter, it's actually not that convenient to do this in functional programming languages. The object orientation in Raku, it's actually very convenient, very nice for this. And so this is one of the reasons I moved to Raku. I would love to move back to Mathematica just because in general, it's nice to have all these solutions in one place, but the gambit here is that I'm using Raku to figure out the grammars. After the grammars, the implementations kind of stabilize. I'm going to have some system which is going to generate the Wolfram language parsers and grammars from Raku. ideally this would be the solution for this. And then Raku doesn't need to be used. This kind of interfaces I'm doing over the web and etc. They won't be needed. You know, they can be native mathematical implementations for this. All right, so I'm not going to expand further on that. As I mentioned, there's a call for collaboration with this presentation, which is close to an hour. It was longer than I expected, but I'm very interested in extending this system with other languages. So right now I understand or parse Bulgarian in English, right? I would like to add other languages here. The other is that the other way to help is to just use this system, to install it, to try it out, you know, or to try it out from the web interfaces. Unit testing is one of the big things that is needed for, you know, needed for this system, and help is going to be to be of interest. There are some selling points. The work on this project is sort of absolute. If you actually can implement certain workflow, that's transferable. It can be transferred to other systems. And another thing is that this system is very modular. None of this, you can use the classification module, which I was showing here earlier, right? Like this here. You can use this classification module by itself. You don't need to use the whole system. You can just use this classification module, or similar, just the quantile regression module. But of course, at some point, it might be nice to combine, and there's a combination. There's a package, Raku package, which combines all of the machine learning modules. But that's also not necessary. My future plans is, this is very Wolfram language specific, using the Packlets, but finishing the book by the end of the year would be nice. There are a couple of things about questions I anticipate, and I'm not going to cover. I covered many of those, but one of the questions here is this a product? Well, yes and no. I mean, it's a product in the same way Unix is a product. It's a platform in which making some products is going to be convenient. I don't necessarily want to sell this. I use this system to speed up my own work, and I mean, if we say if this is a product, this is more of a certain desire for some kind of focused effort. And yeah, focused effort can happen. We take certain subculture of machine learning or any kind of computational workflow like image processing or whatever, and then we develop a domain-specific language for it, natural domain-specific language for it, and then we implement interpreters in variety of languages, or just one, which is, say, most useful. I have covered actually most of the other questions here in some of the previous discussions. I kind of digressed and, you know, hand waved, but maybe this one is kind of more important. What is not covered? Well, yeah, I mean, I would like to kind of use this system into other types of computational workflows like scientific computing, and I showed that for epidemiological simulations. I can do something very similar for numerical integration, and I'm not speaking differential equations, I'm speaking about integration, like the mathematical integration. And as I mentioned, it can be done for some other things, like, say, you know, large-scale air pollution simulations or underwater explosions or whatever simulations, right? So this is some of the things which are not covered by this work. This is much more about machine learning. And references, you can see a variety of references here. All right, thank you for your attention.